this is something I was thinking about because it gets kicked around a lot in scientific circles. That's this problem with the image reversal in a mirror. And one of the questions is, why is the left and right reversed, but not the top and the bottom, right? So there's what I think two solutions, two ways of looking at it. One, I graphed this here, which is, let me see if I put it there. Okay, that's you on the bottom. You see you got your left and your right, and your front and your back. Now, on the top right of your screen is what we actually see in the mirror. You actually see the fronts are adjacent, the lefts correspond correctly, the rights correspond correctly, but the back has been sent all the way to the back. Okay, so if it was actually going to be a one-to-one corresponding reflection, it would look like that image on the upper right of the screen, where the backs are in the same relative position, the fronts are in the same relative positions, the rights and the lefts are all in the same relative positions. So that's a simple schematic of what actually happens. You see the front and the back are reversed, not the left and the right. So when you reverse the front and the back like this, you get what looks like a person in the reflection who's holding up their left hand when you're holding up your right hand. You can do this just by having somebody stand in front of you, and if you raise your right hand, if they're going to pretend to be a mirror, they have to raise their left hand. So this is sort of a simple schematic of what's actually taking place there. On the upper left, you got the fronts reversed. The actual mirror, if the mirror was not going to change any of those axes, then it would look like this one here on the right of the screen. I guess it would be the right of the screen when you look at this. And what you would see is, when you look in the mirror, you would see your back. Your front would be facing away from you, but when you raised your right hand, the mirror in the image would actually be raising the right hand, just like you are. But what happens is the image is raising its left hand when you raise your right hand. So that's like a simple schematic to look at how, what actually is happening. So the image in the mirror is not really, you can't really say it's you. It's the light that's being interfered by your presence, and at the plane of the mirror, that's what the light, the image that the light constructs from bouncing off you. So it's not really an accurate image of you, because it would be like you with your left and right hands switched, which is kind of impossible. Here's the other solution. This is the schematic's a little harder to see, but that just shows you how the light waves bounce off from your right and they go into your eye, and they bounce off from the left and they go into your eye, and they bounce off from your feet and they go into your eye, and they bounce off from your head and they go into your eye. And on the bottom there's what you would think that would look like. You would have you'd be upside down in the mirror, but in fact the mirror image is like what I have there on the bottom. So anyways, that's like somebody would say, well, this schematic here where you're changing the axis is an unnecessary complication, but it's not really. It's really what's happening. The image you see in the mirror is not really you. It's just what happens to the light waves when they bounce off of you and they intersect that plane where the mirror is standing. So that's just for food for thought and something that's fun to think about. Now this is also something that's fun to think about. This is the old 4-color map problem. And you see I got the 4 colors there. And 4 colors is the minimum. That's the minimum amount of colors you need to draw a map, 2-dimensional map, without any of the colors overlapping. See, there's nowhere where the same color touches itself. Okay, if you have the different units, and so in order to do that, you only need 4 colors. So my question is this: let's suppose you tried the same thing in 3 dimensions. Okay, now here's the question: how many colors do you need to prevent 3-dimensional objects packed together from having any of their surface colors overlap? I mean, they could touch at a vertex like these ones do, but you don't want any of the same color to overlap. Now, how many colors do you need? Now, I have some options here. 4, because for 2 dimensions you need 4. Maybe it's the same thing for 3 dimensions. The other thing is, well, if for 2 dimensions you need 4, then maybe for 3 you just need 2 more, because 2 plus 2 is 4, and 3 plus 2 is 5. Maybe you just need 2 more colors than you have dimensions. The other possibility is 6, because if you needed 4 colors for 2 dimensions, that's 2 times 2. Maybe you just need 6 colors for 3 dimensions. Now the last option, 16, and that's what I think. Right now I'm intuiting. I haven't looked into this. I don't know if somebody's actually, you might be able to go on the internet and find out what the answer, the solution to this is. My intuition tells me you need 16 colors, because you have the minimum, the smallest size of a 3-dimensional object. It says here pyramid, 4 sides, 4 2-dimensional surfaces, and if you need 4 colors for 1 2-dimensional surface, I'm thinking you're going to need 16 colors for 4 2-dimensional surfaces to prevent any overlapping of the colors on the surface. So I don't know if this is correct or not. It's just food for thought. Maybe there's a solution that somebody's worked out already. I don't know. That's just my intuition's telling me you need 16, because you got the 4 is the minimum sides for the smallest 3-dimensional object, and so you need 4 times 4 colors. Get them separated. So anyways, that's my little fun diversion for this video, and I'll see you next time. I'm going to do the physics of immortality next.